My name is Ian Craig. I'm from the University of Pretoria in South Africa, and it gives me great pleasure to introduce our first plenary speaker for Ifac 2017, Professor Iven Mareels. He is the Dean of the School of Engineering at the University of Melbourne. He obtained his Master's in Electromechanical Engineering from Ghent University in Belgium, and the PhD in Systems Engineering from the Australian National University. He received civil honors for his work in engineering, education and research. In 2013, the Commander in the Order of the Crown from Belgium, and in 2003, the Centenary Medal from Australia. And in addition, he's won a number of awards. In 2017, just the other night, he received the Ifac Harold Chestnut Textbook Prize. In 2014, he received the IEEE CSS Control Technology Award for work that he's going to talk about this morning. And then in 2013, the Asian Control Association Book Quan Education Award. Iven is very closely associated with Ifac. He was the technical board chair and vice president of Ifac for 6 years. He's also an Ifac fellow, an Ifac advisor. And furthermore, he's a fellow of the Academy of Technology, Sciences and Engineering in Australia, the IEEE, and also Engineers Australia. And then furthermore, he's registered as a professional engineer with Engineers Australia. He's published widely, many books, many papers, and in addition, which is relevant to this morning's presentation, he's a co-inventor of about 30 international patents that relate to the management and control of open channels used for bulk water transport. The title of the plenary lecture is Systems Engineering for Water Networks. Please join me in welcoming our plenary speaker. Thank you.
Thank you, Ian. Thank you. So, as Ian announced, I will talk about systems engineering for water systems, and I've got a subtitle called Measure, Model, Manage. It's easy to remember. It's not measure, model, control, but it's roughly the same. I'd like to say thank you first of all to the organizers for entrusting me with the first talk of the conference, the Ifac family as a whole, because I learned an awful lot from you, and the audience for turning up on a Monday morning with a bit ironic raining when I'm talking about water shortages. My teachers and colleagues, University of Melbourne in particular, that has supported me over the last 2 decades with this work going on. Students and collaborators on this particular work, and I would like to single out particularly Professor Michael Cantoni and Professor Eric Weyer, who have been really instrumental in driving the research in this area. Company Rubicon Water, which most of the data that you will see today are derived from, and also the one that are commercially implementing some of the technology. And of course, we wouldn't be here without significant support from the Australian federal government and the Victoria state government that pour money into our research and enable us to do something meaningful. The talk today is about this map, essentially. It's a map that represents the water stress in the basins around the world, and the darker the red, the worse you're off. And you can see that there's a rather large amount of red on that map. And if you ever wondered why we sometimes call this era the Anthropocene Age, I think this map more or less tells the story. 95% of all the river basins in the world are being overexploited. Some of them are really overexploited. More than 50 to twice as much water is extracted from them as nature can actually provide. Most of that water, actually 70% of that, goes into our food. And so, in a nutshell, if we can't change this picture, we are going to significantly go into trouble. Actually, the 2030 Water Report, we'll talk a little bit later on, tells us that about 50% of our river basins will have significant water shortages, and it predicts 50% of the world population to be in the same space as a consequence. So this talk, in a way, is about systems engineering to reduce water stress. But that in itself is a goal that you can never get any money for or be funded for. What you can do is to probably focus on the reasons why you want the water and reduce the water stress. In the first instance, we want to have twice as much food as what we have now, in large part due to population growth. You want to do that in a way that it doesn't cost the economy too much, Otherwise, you impede economic growth and other priorities will take over. And finally, it's very appropriate to think about that. The rain comes from the sky. Sky is influenced by climate change. So how do you adapt and make this whole thing resilient to climate change? So my key messages for today, if you don't remember anything from the talk except these, would be fantastic, is that actually our system thinking, the feedback and control that we do in our community, can make a difference on the geoscale engineering space. And we can see it as a positive force in the Anthropocene era. A maybe negative message, but a message that is important nevertheless, is that you can't have impact unless you can unlock the productivity key in your era. And the most exciting, I think, is that we as a community have a most fantastic time in front of us. I think from all the time that I've been with the Ifac community, it's now almost 30 years, this is the most exciting time. The opportunities that we have in front of us to create autonomous behaviors using a combination of sensors, communication systems, computation systems, actuators, and the physical environment, and not to forget the human in the loop, has never been as large as today. And in some small sense, this talk will illustrate what you can do in this context in the area of irrigation and agribusiness. I'll have a small video to try to introduce you to the topic of irrigation. It's about this area here. I live in Australia, somewhere south, 24 hours flying from here, in this little green area. I think you can, my map, you can't see my mouse. That's interesting. Well, if you look at the orange part on the left-hand side of the screen, that's Australia. The green part is Victoria. The little light yellow part is the area we're going to talk about, and it's this Goulburn Murray water irrigation district. It's about 500 kilometers wide, about 250 kilometers north-south. About 20% of the land is irrigated, 250,000 people, so not a large amount of people, but an awful lot of farming. 6,000 kilometers of irrigation channel. It's a medium-sized system. There are systems with 40,000 kilometers of channel in the world, and it uses about 2.7 gigacubic meters of water a year. That doesn't mean much to me, but it's 6 times the city of Melbourne, about 2.5% of what France uses, and it represents about 0.1% of the world's water agriculture. Nevertheless, according to the United Nations, you can supply 150 million people with their yearly water supply using that amount of water. And from an economic point of view, it's about 30% of Australia's total produce at farm gate, about $15 billion. So it's about that system that you're going to see a small video that will try to explain what we're talking about.
Smartwater Technology is revolutionizing the operation and management of open canal irrigation water distribution systems around the world, reducing the massive amounts of water lost in transit from storage to farms. Using the world's limited water resources efficiently is becoming increasingly important as the world faces scarcity in many regions. With 70% of the world's fresh water used for irrigation, authorities are looking to reduce water lost in inefficient irrigation infrastructure. In Australia and around the world, canal automation is being implemented to reduce these losses and secure more water for productive uses. In one of the leading projects of its type, the Northern Victoria Irrigation Renewal Project, or NVIRP, is underway in Australia's Murray-Darling Basin. It will secure the future productivity of Victoria's food bowl irrigated agricultural region, while delivering major environmental benefits. The project is automating Goulburn Murray Irrigation District's 6,000 kilometres of canals, and together with targeted remediation and rationalisation, it will see over 425 gigalitres of water saved each year, a figure similar to the amount of water consumed by the City of Melbourne's 3 million inhabitants. Previously, the district was losing massive amounts of water through leakage and seepage, inaccurate metering, and poor control that results from manual operation. It is now being transformed into a modern and efficient supply system that makes the best use of precious water resources.
Water. So, first of all, I would like to set straight that there is no water scarcity on Earth, so I'll talk a little bit about that. Then we look at what irrigation does and what we can do with irrigation through measure, model, manage, and then maybe look at some next steps as time permits. So first of all, there is plenty of water on Earth. After all, it's called the blue planet. There is no such thing as physical water scarcity. To just put it in context, if we could only use water once and then throw it away, it couldn't be used again, our society, as it is now, could go on for 10,000 years. And we would not run out of fresh water. And if you had run out of the fresh water, then you could use your brackish water, translate it to fresh water, and then you had enough for another 100 million years. So that's the amount of water that's available. And given that we never destroy it in normal circumstances, we have plenty of water to work for. So any talk about water scarcity, like what that map suggests, is actually an evidence of mismanagement. We take water for granted and we don't invest enough in it. So we see actually economic and regulatory failures in a systemic way. The other thing to remember is that, of course, this is of the whole world. It's not always easy to get the water from where you want, so spatial and temporal effects are very important. And after all, that's what irrigation is about. It's about changing the temporal vagaries of rain into something that's more reliable, both in space and time. And you want, of course, to look after people. The affluence of people, it makes a big difference in the way the diet is going to move from vegetarian to more meat diet, and of course, climate change. 2030 World Water Group report came out in 2010. It's probably still the main document that indicates the economic failure in the market, indicates a significant shortage of supply if we continue under the no-change scenario. That's the no-change scenario here. You can see about 4,500 cubic kilometers of water being used, 10% domestic, 20% industrial, 70% agricultural. And that's going to move to about 6,900 cubic kilometers under normal circumstances. The bad part of that is that there is no 6,900 cubic kilometers planned. So actually, the only thing that we really reliably have available is 4,200 over that period of time. And that means that most basins, the big blue dark column in the middle there, 2,800 cubic kilometers, in fact, is due to basins with deficits. So we're actually taking more water out of the environment than the environment can sustainably supply. And there are a few basins with surpluses, which leaves us with 4,200 cubic meter available. So the bad part of that is that by 2030, according to these predictions, half the world's population will experience what is called annual water stress. There are periods of at least a month in duration where the average person will have less than 50 liters per day available. So normally, if you live in New York, you use 500 liters a day. If you live in Melbourne, you use about 300 liters a day. So that's roughly 6 times less than what we are used to in the Western world. And more badly, it makes a mockery of the United Nations millennial goals. At this point in time, we have 1 billion people that have continuous water shortage and water stress. By this model, it would go to 1.5 billion by 2030. So food is the most important part of that, because 70% of all the water extractions from the environment go to food production. And if you look at what we need in food, and over the next 25 years, humankind will produce more food than it ever has produced in its entire history. There are about 3 models that say roughly the same. The Seelix Model, which is kind of interesting, it's the International Institute for Applied System Analysis in Luxembourg. They claim that we need 100% more food per annum and 100% more calories. Babcock in Ohio State University claims it's 100% more food, but not as much calories. He claims more vegetarians than meat eaters than the Seelix Model does. And the European Bank is the most optimistic in a way. They think that we can get away with only 60% more food and 60% more calories, and that's in line with the 2030 World Water Group report. But underlying all of these models is one rather remarkable fact, that we don't have any more water, and so all of this productivity gain in the food we have to do with just the amount of water we use today. And that has never happened in the history of our planet. So the question is it feasible, or is it just wishful thinking? Well, luckily, nobody really cared about water. So the opportunities are large. And here is a graph that indicates how much water we lose on average, give and take a few percentages, in the main channels. So that is just in distribution of water. That is taking it out of those big dams, taking along the channels and getting to a farm. If you live in China or India, you lose 60% of all your water just in transport. If you live in Australia, it's about 30%. And where we would like to go to, and if we could get there, the fully automated little green blob on your left is a modernized Australia, which we claim that we can get roughly to 10%. But so there's a lot of water, actually enough water there, if we could just get rid of all of these losses, to actually maybe make this target feasible, no more water and yet double the food. As you saw from the video, we basically used technology of 3,000 years ago. The Sumerians knew how to do that. The Egyptians, 3,000 years before Christ. Basically, it's all manual site operations. People drop pieces of timber, in this case, in the water, in order to stop the flow. Farmers have to wait 3 days on their water. They make an order, and then they don't know whether it's going to happen or not. And that's related to the fact that these systems are large. It takes a drop of water coming from a dam to your farm 30, 60 days in cases, sometimes 3 months. So the risk remains with the farmer, despite the fact we've reduced the risk, and that's why we build the irrigation system, the risk remains with the farmer. On top of that, most systems have very poor water regulation. That is bad because if there is too much water in the channels, because it is gravity fed, that means that the water flows further and therefore you lose water on your farm. It actually goes to the drain rather than on the farm. And if you don't have enough water, it doesn't go far enough and you get mud holes on your farm rather than a nicely spread out farm. So the level regulation is actually the most important quality of service that you have to do in flood irrigation. And then nobody really knows how much water is in these systems. So there's very poor accountability, and you get this fighting between ecologists and farmers non-stop as a consequence. So in a nutshell, if you look at the top system, you take some water out of a dam, say 100 units of water, less than 70, and I'm optimistic here because in most countries it's less than 30 at that point in time, arrives at the gate of the farm. And then because we don't time it properly, the farmer loses another 30% at least, so we roughly get 40% of the water to the plains. And then a plant can only store about 1% of that water due to the normal cycle of breeding, essentially. That's what happens. That's how we actually get our water into our food and in our clothing. We're doing it that way because it doesn't cost us any energy, it's very cheap, the sun does all the heavy lifting, and because of this mechanism, we do have more reliable water supply and therefore a better productivity. And in fact, across the world, 50% of all the farm profit comes only from 5% of the farm land, and that 5% is the irrigated land. So, what can we make a difference here? And how can we make a difference? So for that, I would like to look at the timescales and the dynamics, if you like, of the system that we want to work with. And I've got here a line in years, logarithmic, so 0 means 1 year. That's probably the main time scale that we're talking about. And then I'm going all the way down to seconds, and you will see in a second it actually will go even lower than seconds in order to make the system work. And that gives you a bit of an indication of why it is this era that we can actually do something that nobody else could do before us. So the longest time scale is groundwater, and that's why groundwater actually is really non-sustainable. Groundwater interactions, for example, the travel time from groundwater from the north of Australia to the south of Australia is 1,000 years. We shouldn't actually intervene with that too much. Most closer to home, farm planning and so on is in kilometers. River-soil interactions up to 100 kilometers, 10 years, typical dynamics of these things. And of course, the hydro cycle works on a yearly scale. The actual physical movement of water, the turbulence that is driving all the water molecules around, works from the molecular level all the way to distances of 10 to hundreds of kilometers, and you can see that in big rivers, how turbulent structures actually are constructed and persist sometimes over days and weeks. It's there that you actually start having to measure. So you will see that in order to actually get to water flow, we have measurement instrumentation that has to work on a 100 nanosecond time scale. Our infrastructure we built typically is planned for 100 years, but if you only look around in Europe and some of China, India, Sri Lanka, you will find infrastructure that's 1,000 years old and older. Water travel time already talked about, a few months. Our control that we're implementing right now, all the way back to 3000 before Christ, typically weekly schedules, sometimes monthly schedules, all linked to periodic scheduling of water manual operations. Yet water levels and flows in our channels behave in hours and days timescale. So you can immediately see there is a mismatch between the control that's been implemented and the dynamics that is available. So we can only do steady state control if you like, and in practice there is actually no steady state. Our models that we're going to introduce will allow you to describe more or less how these channels behave over a few minutes to probably up to a week and a month. And that's where we're going to focus on. And our control strategy will be to focus on the water level regulation and get that right, and that is intervention in the order of minutes, essentially. So all tells you basically that there's opportunity here for us to do something. And then we have to manage it all and make results out of it on a long-term basis, and for management it's actually important that we get a data-based, evidence-based information about the economics of farming. So in a nutshell, poor water management actually comes from the fact we don't know where it is, so we don't measure what we want to manage. And we have manual operations that look at steady state rather than at dynamics. So we can never take an opportunity like what is in storage in the channel available, make it available to us, because there is simply no control to make it relevant. What we want to do is regulate the water level so that the farmer has the right amount of water on his farm and doesn't lose it. We want to regulate the flow from the channel into the farm gate, and that's particularly important when the farmer has already invested in pumping infrastructure. And we want to, most importantly, you will see that in a second, give the water when the plants need it. So I would call that watering on demand, not on a schedule basis. And that's what we're going to try to achieve. For that, we have to bring in some new measurement devices to make this work. And our team has worked on these gates that are both an actuator, we can close them, change the flow, and as well an accurate, relatively accurate flow and level sensor. It's self-calibrating because these things are installed in farming environments, so not necessarily a laboratory environment. So there's a lot of thinking to go in there to make sure that what it measures is actually what you think you're measuring, and that it actually also actuates the way you think it's actuating. A nice feature of it is that the gain of the controller is super linear, which means that big control actions come a little bit easier than small control actions, which is an important thing because irrigation channels often run at close to full capacity. And a big issue for control will be that these systems are saturating both above and below. You can only get a gate open or close it, and in between, of course. In itself, the gate has a lot of measurements for water levels, downstream and upstream. You have temperature sensors for compensating for expansion and temperature effects. You measure extremely accurately the position of the gate because in the end the flow is a function of the geometry of that gate and the way that the flow operates. And you do that quite accurately. And there are quite a few extra devices there to help us to eliminate any backlash in the gearbox, etc., to make sure that when we position the gate that we know that we position it the way we wanted it to be positioned. The ultrasonic, and that's where the very high frequency effects come. In order to measure the water levels, we use ultrasonics, 4 megahertz transducers. We use them left and right of the gate, so there's a bit of redundancy. We can lose a few sensors, but also the redundancy helps us in general to make sure that we know whether the gate is positioned straight or inclines to the left or the right, because that will tell us something about how those measurements work. And then we can compensate for it. And we also compensate for the temperature effect in the speed of sound and so on, in order to make it work. And in the end, we have to make it work to about 0.1 of a millimeter accuracy for the water levels, and that's after we take waves out and things like that, for the average. So we have ultrasonic transducers, angle encoders, magnetic pickups to know that the gate is actually working the way we think it should be working, temperature sensors, inclinometers, and they're just the devices that we use for the actual flow measurements and for the level regulation. There are many more variables that we keep track of with respect to the energy in the battery and the solar radiation that we use also for farming advice. In the end, we can get the flow level to within 5% across the full range, and about 1% or less above 0.6 of the maximum flow rating, which is actually the place where we normally operate. There are all sorts of alarms when things go wrong, because with so many gates in operation, the fact that there are about 4 or 5% of your gates having errors or alarming is not unusual. Once you have that data, you can start thinking about what you should model and how you should model it. And in principle, you go to your textbook and you will pick up the same Venn equations as your shallow water equations. But when you go there, it becomes all a bit complicated and difficult to implement in the field, especially if you start thinking about having to link about 10,000 same Venn equations with all the boundary conditions we don't know, etc. So in the end, we do some gray box modeling that we adaptively track during seasons to make sure that our parameters roughly reflect what is happening. And what we try to model is essentially the preservation of the potential energy, or if you want, the mass balance equation, roughly the same in this case. And we also look after the first wave, because we don't want waves. Waves are the pest on these channels. They cause all sorts of troubles for maintenance, but they also cause losses that we don't want. So we want to know what the waves are, and we want to avoid them. We have a bit of a delay on each of these channels, so that is normal, because when we open a gate, the inflow into the next channel, the next pool, will actually affect the downstream water level with a certain delay, which is related to the wave speed on the channels. And we have a relationship between the length and the depth of the channel that tells us about the delay. Unfortunately, nobody knows what those channels really are. The surveying of these channels is probably more than 100 years old. In the meantime, things have changed a little bit. So we have to track that adaptively in order to make this work for us. So the model here consists of, on the left-hand side, the I minus first pool, if you like. We know what the water levels is there. We know what the flow is going into the next pool. Then we have a pool where we measure essentially the downstream water level. And that's the water level we want to control and regulate, because there is going to be the main offtakes for the farms, most likely, and also going to be the main offtake for other channels, if there are other channels taking off. In the end, you get almost a linear model if you linearize the gates that are nonlinear objects, the flow out of the system. And the other thing that you learn, of course, that there is a significant disturbance, because farmers taking water out, but you're also losing water out of the channel through evaporation and seepage, and those things are not easily measured. We can derive them, but they're not immediately available, and therefore we treat them as disturbances. Then you have to put them all together. If you talk about a system that's 6,000 kilometers long, you roughly end up with around 10,000 of these pools, and you concatenate them according to the topology of the network. And essentially, you get all these variables, the upstream gates, the downstream water levels you want to control, and they have a disturbance due to the outflow of the pool, of course, and the offtakes that come in. And that's your unit, essentially, and that's the unit we have concentrated on. We have made a choice. We have taken the upstream gate and controlled the downstream water level. It's a choice that we have evaluated why it's a good choice, but in principle, that pairing of variables is an open choice for you in your control environment. We have just chosen this one because we believe it works reasonably well. Then we control that gate, the upstream gate, in order to maintain the water level downstream, and that water level comes from somewhere. And in principle, it comes from the heuristic that we know how to operate the system, but it's a variable that you can set and we can actually play with, and it would be very interesting to play with that if you want different regimes in your system to be controlled. For example, you want to maybe a flood mode control where you want to let water flow through the system as fast as possible. That will give you a different set point than what you want to do under irrigation control. That's a global variable. That has to be set somehow, and it's set in this case because of the vastness through a radio-based IP network. Typically set for a whole season, so we don't change these variables a lot. Once a while in a season is basically it. Then locally, we need to know information about the downstream gate. So the downstream gate has to talk to the upstream gate, and that also goes through a radio uplink. It's a very simple communication, doesn't require an awful lot of information exchange, and it's all done by event-based. So nothing is done regularly. It's just when something changes, we let know the people that need to know. The advantage of this is that you can retrofit, it can scale well, it's totally decentralized, and the local controller can act as a lone-standing controller, knowing what it has to do, regulating a flow, given disturbances that come in play onto it. The supervisory control problem of setting the levels and maybe the flows at the gate of the offtakes, it's a more difficult problem, and that typically approached to an MPC problem in our thinking, but often in presence in the management is done basically by heuristics. So the other control variable here, the news on the bottom, are basically offtakes that the farmers have ordered, and they are global variables, and they have to communicate it to a global network, and they are very often much more frequently than the set points themselves. If you don't have that available, if you don't get that communication, the controller will simply take it as a disturbance and then act on it through the level controller itself. Inside that box, we have basically two controllers. One that looks at the water level, that's the main one. He wants to make sure that the farmer gets the right water level. That's the level C controller. And then we have a flow controller, one that knows what the next gate needs in terms of flow and then ensures that at least that flow is passed through the local gate so that we can satisfy downstream demand. The green dotted lines indicate local communications. The red dotted line means global communications. And in this case, I have basically taken the offtake information from the local pool information, so without having the global communication. So there's a bypass, if you like, but it's slower bypass. If you don't know what the farmer is doing, you can always measure what the farmer is doing through the local system, and that's the way it's mainly implemented. At each local gate, because it's a saturating controller, actuator, you want to, of course, some anti-wind-up. You do some nonlinear model inversion because the gate is a nonlinear device. And you do also suppression of waves and rate limitation in general so that nothing moves too fast on these rather slow systems. So far, so good. That seems to be reasonably working, and we can do reasonable designs with these. But not everything is a tree. Canals branch, canals join. And then you have to make some more choices. And if you make all those choices and want to make all those choices, you very quickly get into a combinatorially hard problem. And what typically is done by management is that they take a heuristic approach and they cut these NP hard problems and say, well, we'll take this as a slave and this as a master. And that leads to suboptimal solutions in many cases and some problems that is still not worked out. So this whole problem of topology and how you select topology and how you have variables paired remains an open and interesting problem, and I think in most large-scale systems actually an important problem. Even in grid control, the same problem occurs, and we have some heuristics by which management approaches this problem. Doing this more properly, more scientific, is an open problem. The choices that you should make would like to approach a global solution, but for the moment, nobody knows what a global solution is, and so therefore we don't have proper choices. So from an overall control design, there are actually three levels of control. One, the long time scale is implemented, be it manually, is a managing controller that checks whether everything is working well. And typically you do that over a season, and then you adopt your model and your control topology as required to push harder your assets and getting better water saving, because that's your main target as manager. In the middle is a controller that you would like to have implemented, we have worked on, but we actually have not in the field. The supervisory controller that plays with the water level set points and adjusts those water level set points to the scenario of operations of the channels, whether it is a flood control or whether it's irrigation or whether you want to do a rejection, or like filling the channels or emptying the channels. That's not implemented, that's all heuristics at this point in time. And the other one that is quite interesting that is also not implemented at this point in time, partly because it's not really necessary, although in some systems where it's heavy use, it is becoming very interesting, is actually to do rescheduling. So how can you delay demand in order to meet the supply? And for the moment, we try to meet demand just by stochastic and first come, first service, and an economic argument that if there's congestion, we put the price up of the water, which is basically what is happening right now. And so people drop out of the market and therefore make everything workable again. And that is implemented now. But there are better ways of doing that. We'd have higher water savings opportunity or higher economic gain, but then rather than using a price. And then finally, the bottom level controller is the control that is implemented in the systems I'm talking about. That is where you do the flow control on the gate to the farm and the water level control inside the channels. And there's only one design issue that is really cumbersome in that space, and that's a design issue that comes from scaling, is that you have a chain stability problem. If you push somewhere, there is an instability. The gates will amplify that instability by the simple fact that you have an integrator and a delay, and so therefore you always have a gain amplification around DC. So you always have to worry about that problem, and you do have chain instability problems that you have to overcome, but for that you can use design rules and heuristic rules that allow you to avoid that. So bring it all together, you get an Internet of Things for water management, a SCADA system that we've integrated all the way from the downstream water controllers to the management and the accounts of the water pricing and everything else. It has the sensors, the actuators, the wireless IP network. You have management and the farmers all interacting with it. In the end, it's a fairly large software system, about 70,000 function calls. And just to put it in comparison, that's about 50% of a SAP system, about 100 times more complicated than the Windows operating system sitting on my computer here. But not to burst our bubble, but less than 1,000 function calls are to do with control, signal processing, and modeling. The rest are basically the accounting and the asset management things. Despite the fact that it's called a large database, a large data system, it actually is reasonably easy to control. In the end, Goulburn Murray Water has about 10,000 states, about 300,000 control states. We track about 1.2 million dynamic variables and about 2 million static variables. They can change over a season, but not faster than that. So 3 million variables, say, the dynamic variables get about roughly 10 events an hour. So with 300 gigabytes of data, you're done a whole season. It's not much, right? So you can easily cope with that, and you can manage an entire system with relatively good information you had never before. And how it works is a bit like this. The farmer on your bottom right can make a decision to irrigate. You will ask the question. The HQ will compute whether that question is relevant, can be met. If the farmer can get the price that he is interested in, if it's not possible, they will tell him what the price is, which time the farmer can decide to accept or not reject the price. Or if the farmer insists that it's part of his priority allocation, the system will then go back and seek out when it can be implemented. It basically runs the model forward in time, fits in the farmer's request, and typically within 20 milliseconds, the farmer will get an answer on when their water is available. And for 95% of the farmer's request, this has turned out to be less than 2 hours. And you have to compare that to a 3-day typical delay time. 2 hours, 1 hour is very common. Very rarely that a farmer has to wait more than 1 day. Once an order is accepted, the HQ system will set up all the regulators along the channels and command the farm gate to deliver the farmers the water as requested, at the flow requested, for the time requested. That would give you on-time delivery as the farmer requested. What is really interesting, and I can't talk too much about, is that actually you shouldn't trust the farmer, you should trust the plants. The plants should tell you whether they are thirsty and whether they need water or not. And so on-farm automation to actually determine when is that time that you need water is actually one of the most important contributions to productivity on the farm. And for that, we have farm sensors that look at how much evaporation, what are the plants doing, how much water is available in the root zone, how fast is it disappearing. Combining that together with the model gives the farmer much more control over their farm and actually enables them to grow much more food with the same amount of water. That all automation can be integrated with the channel system, and then we have a totally closed loop, almost autonomous watering system where we have humans in the loop interacting with both, do I buy water or not? And so the financial decision and the management decision, can I do this or not? If you look at it that way, in principle, we can cut out about half of the losses. Basically, the losses we cannot get rid of course, are the seepage losses. Nothing in control can do anything about that, and the evaporation losses. But they amount only to about 10%. So if you release 100 units of water from a dam, about 90 will get to the farm. And then if the farmer gets the water right as well, then the plants will actually absorb most of it as well, and they will get to 80 units of water to the plant root zone, which in principle would give you about 100% productivity gain on the farm. And that's really what we're aiming for. And the advantage of this system, of course, is totally energy footprint has not changed. So this is purely playing with the timing of water, and a bit of storage in the channels can make a significant difference. When you implement that, here are some of the results. This is the Collie region, it's a smaller region just to the north of the system I've shown you. The red line is what happened before our control implementation was done. So we're running at around 100 gigaliters of losses a year. The allocation there is 300 gigaliters, so they lose about 30% of the water, so it's not a bad region. It was actually one of the best regions in in New South Wales running it, and they're mainly having crops of barley, rice, and cotton. So not precisely the things that you would expect to grow in Australia where you have water shortages, but they're doing it very well. Total system, 500 kilometers of channel, 4,000 kilometers square irrigated land. So it's about 20% of the Murray-Darling system, the global Murray water system. They have achieved better than 2-hour lead time, and they're now running at 15 gigaliters of water, which is really roughly what is evaporation and seepage like, maybe about 10% above that. Over the years, they have seen continually how to improve their operations, and that's basically the management playing with the water level systems and rustically adapting their rules of operating the system to get more and more out of it. And they had a major upgrade in 2014, and after the last 3 years now, they have actually run at 17 gigaliters of losses. So a significant improvement for the system, and they claim, probably rightly so, to be the world leaders now in managing a large-scale irrigation region. The farmers are extremely delighted. That was the management perspective, but the farmers actually are even more delighted. Typical there for the grains, so the rice, the cotton, the rice and the barley, corn, probably in their manual operations, they were extracting about 12 megaliters per hectare. They're now extracting 7.5 megaliters per hectare. That saving remains with management. So the management sees a reduction for their barley growth of 40% in water consumption. The farmer pays for about 20% less, and the plants get about 20% more. And because of the timing, the yield is dramatically up. So the yield per ton per hectare now in that region is 27 tons per hectare, which is amongst, well, it is the best in Australia. And the yield per megaliter of water is 4 megaliters of 4 tons of barley for every megaliter of water, which is more than 100% better than what they had before. So the saving that you get from the dam, you can use to all sorts of things. And management is actively talking to the environmentalists to see what they can do with this water to have other uses. Of course, the farmers say, but hey, wait a moment, I want to pay for that, but I want to grow more rice. Maybe not the right thing to do. The most important thing for getting the yield right is the timing from plant feedback. So these farmers we're talking about here actually have on-farm automation that tells them how much their rice and how much their barley needs in water, and it's the timing of those sensors that tell us when to arrive water there. And that gives them the superior yield. If you take that out and you compare with the farmers that have not implemented the on-farm automation, they basically are about 40% better off without the automation, but with the automation, they're about 100% better off. So it pays to have the automation on the farm. And if you ever want to see a difference between open loop control and feedback control that is very simple, here's a very simple example that really shows how feedback makes a difference. And in payback time, the farmer has to invest basically a year of their extra income in order to get the automation going. So it's not a big push to get the farmers into this direction. So where are we going next with all of this? Well, first of all, this gives you a bit of an overview of where we are. We haven't done an awful lot yet from the market. The dark blue dots are indications that there are commercial implementations of both the on-farm and the large distribution networks, and it's mainly in Australia. Big important dot, and one where they actually didn't need it, but the New Zealanders have implemented in their dairy region an entire system. The north system is fully automated, and that's partly because they just want a productivity gain. They want to keep on top of being in the market as the world leader in dairy production. In China, we just have signed a big deal, the Rubicon has, to do a automation on the Guangxi province, just in the middle of this dirty red dot in China. It's blue and yellow because some installations are already there, but the opportunity over the next few years is absolutely massive. Only the channel automation, not the on-farm automation, partly because the farmers there are too small to really look at the benefit of significant investment. And so we'll have to convince the government there to conglomerate farmers together to invest on behalf of the community in the on-farm automation to get that extra efficiency gain out again. South of California, north of Mexico, part in Chile. Although in Chile it's not what you would think, it's not to do with agriculture, it's actually to do with mining, the installations there, and significant opportunities in Italy and also Spain. The yellow dots are places where we're talking to, but there's an awful lot of work to be done. It's going very slow to me, in my opinion. We only have about 5% of the world market addressed. We have saved 1% of the world's water a year. That's 45 cubic kilometers. Remember, we need to save about 2,000, right? So there's a lot more work to be done. I'm not sure whether the time is on our side. So although we're making progress, I do think putting our heads together and getting more people involved would be a fantastic opportunity. Ongoing work, side effects that management very much likes. How to maintain these channels is not a simple task. Leak detection is a big deal. Here you can see a leak that is made by a small animal, a yabby. Farmers will not complain because they get free water. But your management system will know that there is water disappearing. So finding a leak is not such a big deal. The software, the water balance actually tells you that the leak is happening on that pool about 3 kilometers long. You can walk it and find the leak readily. So that's one way you can improve leak detection. You can also identify which of the pools are actually giving you the most trouble in terms of losses, and then you can remediate them so you can direct your assets, money, in a better way. And in principle, what we found is that about 20% of the pools account for 80% of the losses, typical 20-80 rule. The next step of how to use that water better and do real model predictive control is still an argument that we're having with management to see whether we can implement that, and hopefully with Coriamboli we can take the next step. My real dream is to do next scale up, basin scale water productivity. We can't do that in many places because of international treaties and so on, but water needs to be managed at the scale of a basin. That's all your natural rivers together, your groundwater, your dams, all the people that irrigate in there, all the environmental needs, all together under one roof for data management is actually the way to go. And it's time and time told so as well to the United Nations reports, World Water Report on this thing, but nobody actually does this. This requires a scaling up of around 30 times in area and about 10 times in time. So it's a not an insignificant step from an integration point of view. And there are an awful lot of institutions whose boundaries are being crossed when you start doing that. But this is the way to go forward. And how we can get flow catchment models that are working over very large time periods together with the short-term models that we have and making these operations seamlessly work is a big task that we hopefully will be able to start doing in Australia, at least for one river, the Murray River. The promise there is, again, productivity. We want to use less water. We want more crop. We want to do more per drop, essentially. And then the Bureau of Meteorology, the economics come into play, and they are going to fund all of this work to be able to manage over this whole thing. And so planning support for crops, which crops would go where do you grow them, even at the scale of a farm, because many farms actually doing monocultures that are not at all the right thing to do for the grounds and the supply of water that they have available. But they don't have the data to make a difference. And so that's, hopefully we can start pulling that all together and make a difference. Something to do with closer to climate change, flood control. Flood control is becoming a significant issue in many places around the world because our rain patterns are changing. Didn't say much about Belgium and Italy, but in principle there, what is happening with the water is that the periods where the water comes, it comes over short periods of time in big bursts. And that means that your rivers can't cope, so you get more flood problems. And the question then is, can you use irrigation systems? Not in Belgium because I don't have them, but in Italy, in Thailand, Bangkok, there are many irrigation systems available, and the question is, can't we use those to help us mitigate flood effects and route floodwaters through irrigation systems well in advance of floods, and we can predict floods. So that would make a huge difference. How to implement that is further steps. Then in general, data mining for agribusiness and providing agri-support from all the data that we're gathering, and we have data about all things from plants, how they grow, what sunlight they get, the averages of their soil conditions, and using that and data mine that in order to provide better service, certainly something we want to try. Just to show a little bit about that flood control problem, here is a picture of what happens in 2007, the Glen Maggie floods, about 60 kilometers southwest from where I live. At the last minute, they had to open Glen Maggie Dam, and within a few minutes, the pump house that you can see on your right disappeared under the water, and our gates also disappeared. You could just see the radio antenna on top of it. But on your left, you can see if those gates were not working. Actually, there was no irrigation required. It was raining, so why would you irrigate, right? But those channels can displace an awful lot of water. And if they had been open, and had been open for a while, we could actually disperse the floods over a much larger area than what the riverbanks would allow for. And now the riverbanks were significantly damaged, about $60 million, may not sound much, but that was significant, $50 million by insurance cost. Back of the envelope calculation showed as if we had acted one day earlier to open up the irrigation system, we might have basically avoided this flood altogether in the city. So there is some opportunity there, and we're not using it yet. One thing gives me a kick always is when I see actually the people that get the most benefit out of it, and indulge me for 1 minute, a small video from this farmer who tells a little bit how the automation has changed his life.
The way the system used to be, I had a very limited life in what I was doing because I was virtually watering most of the time. But I see with this system now, I'm hoping for another 10 years of irrigation, which is really something. So, can only happen with a system likes of this.
So to put it in perspective, this farmer has been busy for about 30 years on a farm, is extremely good with his farming, but basically by labor limitation, he couldn't continue with farming. Putting the system on board, he will get another 10 years. That's a 30% productivity gain for that particular farm. So that's not me. And it's always nice to see a happy customer of your ideas. So in short, we couldn't actually manage 100% food productivity simply because of some, I would say, relatively straightforward ideas that are available in our community of how to measure, how to model, and how to manage resources. Well, then I would like to finish maybe on one, because Ian hasn't given me the finger of death yet, about the economics. I always get questions about the economics. Now, this is an economic assessment done in 2004 for when we started with the Envelope report, the renewal that the video saw of, and adjusted with 2016 real-life data. We're about 35% of the finish line, so we're about 60% through the whole system. At first, if we did do nothing, it would cost us about $20 billion to clean up the mess that we created, and that's because of basically soil reconstruction requirements. And the crop losses were estimated about $7 billion, and now they're more estimated like $15 billion, but that's inflation for you. The government wanted to buy back about $1 billion in water rights. They've actually bought back $1.6 billion in water rights. That means farmers out of business. And the crop losses, according to that, is about $1.5 billion in losses for the farming community. On the other side, costing the efficiency automation originally was estimated at $500 million. And they were targeting 400 gigaliters of water savings, as you heard on the video. 400 gigaliters was the target. In reality, is we're now going to go towards a $1.5 billion investment, and we're saving 800 gigaliters of water. But what we didn't know at the time, when this white paper was committed, was what it actually would do to the farming community. And now we know that the value of the improved yields in that community will roughly equal 1.5 billion per annum. So that's a significant additional benefit of doing the automation, although that also includes on-farm automation. In comparison, putting this whole system in a pressurized piped network would have costed roughly $15 billion in today's dollars, and you would also have gotten roughly the same amount of improved yield, maybe a little bit more. So that gives you a bit of an idea of what automation can do in the context of irrigation. And with that, I thank you for your attention.